Welcome back to the afternoon session. This morning session was, without a doubt, awesome. And the speakers were amazing. The communication panel, large as it was everything we had ever hoped it would be, and well coordinated by Kelly. So thank you again to the communications panel. This afternoon we have this afternoon, and I think it's tomorrow morning, we have two education panels. We've divided them in parts so that the first panel this morning focuses on basically high school, community colleges, and undergraduates, and then the one tomorrow will be graduate students and postdocs. But as Fred pointed out earlier this morning, it's important to be able to not only communicate issues of mathematics for planet Earth, but to develop an education plan that can be widely circulated that discusses how to best provide either infusion into courses, ideas about how we can begin thinking about it as early as elementary school, but particularly in high school, and how both mathematicians and non-mathematicians can infuse the need and role of mathematics in all of scientific research, but in particular in a great deal of the environmental sustainability research that's being done at the moment. So without further ado, I will have my panelists introduce themselves and say a few words, and then, as occurred this morning, I will ask some questions and they can respond accordingly. So you're first.
Hello, I'm Carlos Castillo Garcia from Eastern Washington University. One of the things that has always intrigued me is this idea that mathematics classes build on each other. I hear this a lot from mathematicians, the idea that you need the skills from the previous classes to go into the next class. And when it's done well, I think it's really a beautiful thing. So we can talk about, for example, how the long division algorithm in elementary school can, in the hands of someone who knows where it's going, become a jumping off point for talking about polynomial division, and then that can be a jumping off point for talking about polynomial rings. And the way that it ties together across the curriculum really has a lot of potential. And then we think about, but that kind of progression for building students into mathematicians really only is designed to build students into very specific types of mathematicians. And there's kind of an assumption throughout the entire curriculum that people are learning math to be analysts or algebraists, when very few of people who take math in school are going to go on to become pure mathematicians. So one of the things I'm very interested in is what mathematics do students need in secondary school, in middle school, in elementary school, though I haven't gotten to that level yet, to become applied mathematicians in a broad sense. What do they need? What do we need? How do we need to sequence things to build better prepared engineers, mathematical biologists, so that we can look at that progression of skills designed to build applied mathematicians in kind of a similar way that there's a progression of skills to build pure mathematicians. So that's largely what I'm interested in.
I'm Katrina Palmer. I'm at Appalachian State. Before I got my PhD, I taught high school, and then as part of my job at Appalachian, I used to coordinate the graduate program, which is geared at training community college teachers. So I'm much more interested in how to work with both high school and community college, and at least in North Carolina, the big push is to have them go to community college before they come to 4 years, so have that transition, and then how do you, I like all the applied stuff, how do you get them students to appreciate it? And I always think we can get them to appreciate it by the applied math. And I personally am very interested. I come from a family of biologists, very interested in sustainable issues. And at Appalachian, at least on our campus, they advertise how well known we are for our sustainability efforts. So I want to think, how do we get the math in there?
My name is David Black. I teach at a high school, a very small boarding school in the middle of Massachusetts, and I am very atypical of a bunch of high school teachers. I'm primarily atypical because I don't have to address all the standards that are coming down. I don't have to address any core curricular ideas, and it gives me the freedom to play with a bunch of different quantitative integrated approaches. I do spend a lot of time working with high school teachers, especially advanced placement environmental science teachers around the country. I've run workshops everywhere, and it is a particularly challenging landscape now for everything that all of you are talking about. Many people have said that they're not mathematicians. I am truly not a mathematician. I stopped taking math after my junior year in high school. I got into college and I had to have Calc 1 to get a biology degree, so I joined the 1,200 other people in the class, fought my way through it. When I struggled because I had never had calculus before, the TA told me to do every problem in the book. And that was not terribly helpful advice, and I think I got my C-, and I think I got to be a bio major by doing that. But it soured me on math in a big way, and as my career has gone on, I spent some time consulting, doing environmental consulting and writing environmental impact reports before teaching. I came to understand the importance of a quantitative approach to ecology. It's very frustrating right now for several different reasons in the high school world. The first is that the standards for environmental science education and ecology almost never contain any mathematical component. The AP Environmental Science curriculum now is completely and totally focused on unit factor analysis. That is the only math in the program. And I'm a reader for the AP exam. 2 years ago, something like 70% of the students taking the AP exam, which in theory are some of our more elite students, simply left the mathematics problem completely blank. So we have the math phobia that several people this morning referred to, which translates into the high school level. The other problem for a conference called the Mathematics of Planet Earth lies in the fact that high school students self-select, and if a student is strong in mathematics and strong quantitatively, they will always take physics. Environmental science is always relegated to the students who can't do math, so any math we bring into them is grossly unfair, and it's not what they signed up for. So I'm here to learn. I participated with some of the DIMAX modules, and I've worked with some other mathematical groups around the country over the years. What we have to do is train teachers to use math to teach concepts. It can't be an add-on to the curriculum. It has to be an integrated part of the curriculum. The teachers have to be trained in the mathematical principles that they never studied because they were environmental science people. And I'm very eager to hear what people have to say. I'm eager to learn about the resources available to teachers and to see what we can do to broadcast them and publicize them more widely.
Thanks. John Junk, University of Delaware. What I thought I'd focus here on this one slide is the biggest problem that I face with educators when they're asked to include math in biology is almost always they think about it as equations. And I unfortunately wrote an article, 10 Equations That Change Biology, and it just reified the importance of equations. So my apologies to you, kind of thing, for doing that. But really, what we need to work at is how do they not just view it as individual activities of what am I doing on Tuesday, but what's the learning progression that you're hoping students to do? And very much like your situation, I worked 12 years at trying to reform AP Bio, and this diagram in the center, we actually got into the AP Bio student and teacher's manual, literally, because trying to move them beyond the equations kind of approach, but also to respect the skills that their students do. The students do come, and biology students, You can ask them to measure and count forever. They're not afraid of those kinds of activities, that graphing activities and so on kind of thing. They are bright enough to get out of the way of Mack trucks. They have some intuitive sense that they've developed some quantitative reasoning. And so we need to build upon the skills and the intuitions that they have quantitatively and mathematically. And by having a learning progression, that what's the metacognitive kind of growth that we're asking our students, our professors to think about in the design of what you're doing within your curriculum over time. And modeling turns out to be kind of one of the hardest things that it is to invoke. You knew your model was false before you ever even tested it, and so their typical Popperian ideas of falsifiability fall apart. Why are you building something that you know is false? And how do you then think about here with issues like global climate change that we're basing decision-making, crucial decisions, based on models? And so how do we need to do this? And so some researchers in science ed, Jim Stewart and Jen Cartier and Cindy Passmore, the How Students Learn, there was a second volumes. One was in mathematics, and this was the chapter on biology, and they developed this. And then Joe Kraychek's group at Michigan and Michigan State very much build on it, that students frequently do model-less problem solving. They don't have a problem. Or they want to know which equation, and they just explicitly applying that kind of model. In some cases, they're asked to compare various kind of models. So I was looking at Kelly's stuff on Simpson's versus Shannon's index of biodiversity. Why would you use one or another? What's the differences between these and so on, kind of thing. That you doing some kind of model revision, and then maybe you add another component, a time delay or whatever kind of stuff. And then finally that students are actually building it. Tony Weisstein at Truman State talks about taking them from kind of the black box where the simulation that all of the mathematics is hidden to kind of a glass box where it's transparent, and we tried to explicitly do this, and Lou actually was the person that stimulated this. He screamed at, you hide too much of the mathematics. So when we did Excel things, the equations were right there, and the students could click on a box, they could see it kind of thing. But then actually teaching people, how do you go from cartooning to words, to equations, to a spreadsheet, to data, to modeling kind of stuff. And Tony has really developed this extraordinarily well. But then finally I wanted to, this other kind of category here, we've talked about citizen science. And unfortunately too much of citizen science is in what we frequently refer to as Bloom's basement. You know, that how do you have this notion that you're crowdsourcing problems and getting students to activity and collect data and so on, but they had no opportunity to frame the problem. Frequently, they're even screened off from analyzing the problem. Very frequently, scientists are publishing papers based on citizen science, and they don't even acknowledge the people who collected it or where it came from and so on. How is it that if we're going to have truly participatory democracy, that we run classrooms not as a medieval kind of authoritarian environment where we're the disseminators and the evaluators of knowledge, but students are democratically participating in the social construction of knowledge and see themselves as knowledge producers? Thank you very much.
Thank you. I think I will expand on what some of you have mentioned and ask if you have ideas basically about how to infuse the combination of environmental science and mathematics, or mathematics and biology, as it relates to planet Earth into classes, whether they be middle school, high school, or college. And are there resources out there available that would help you do it? And if not, what do you need that would help you do it? So.
It's a big question, and I can pretty much use up the entirety of the time that we have talking about it, so feel free to just cut me off at any time. one of the things I think is kind of the big issue is simply identifying what it is that needs to be infused and when and where. And as we've been talking and as I've been thinking about this, I've been creating lists. And one of the things I really like is John's distinction between the distinction that John talked about between model use and model construction. Because too often the scaffolding that students get of, we need to put some modeling in a math class is a model use question, and students get very little practice with model construction. And that kind of topped off my list to begin with. Is one of the first things that students are missing is practice in how to choose a problem. How to choose a problem, how to build a model. And one of the examples I like to give of this for scientists is the scientific method is my worst enemy. Right? The traditional scientific method that you see in classrooms is form a hypothesis, design an experiment, collect data, do the analysis, and then you either support the hypothesis or you reject the hypothesis. And it's missing the most important part, which is how you form the hypothesis in the first place. An example that I like to borrow from Flipberg is the idea of Galileo's experiment, the inclined plane experiment. And that experiment started with a hypothesis that, if I have two things of different mass, they're going to fall at the same speed, essentially. But where did that hypothesis come from in the first place? And where that hypothesis came from in the first place is a thought experiment, right? If I have a ball and I drop it, it's going to take a certain amount of time to hit the ground. Now, if I believe that lighter objects fall slower, what happens if I cut that ball in half? Are the two pieces going to fall slower? What happens if I cut that ball in half and then I stick the pieces together? Right, so that is it still one object? Is it two objects? And we come to this conclusion that the idea that smaller objects fall faster really is about our perception of things as objects. And from the point of view of the universe, object is a very fuzzy concept. Right? So this idea of once you start thinking that way, then you can form a hypothesis and then you can build the experiment. That forming hypotheses is the hard part. Choosing problems, building models, those so-called soft skills are neglected in a lot of classes, and we don't really have a good way of thinking about how you build up a student's ability to do that over time. But we have some ideas, and that comes from some of the other things that, for me, when I'm looking at curricula, are missing. We talk about what do modelers do. A lot of the conversation from the previous group was about computation. And if you look at the high school curriculum or the undergraduate curriculum in mathematics, simulation isn't there. Programming isn't there. Computer science isn't there. Statistics is there, but in name only. So we're missing a lot of the skills that are student accessible that they need to start thinking about modeling. I have a list here: simulation, statistics, big data, chaos, bifurcation, matrix algebra. These are things that students can do, but they're not part of the curriculum, in part because the curriculum was never designed to make applied mathematicians. So, and one of the things that I think is very interesting is if you look at the work of people like Uri Walensky or Mitch Resnick, or some of the work that's going on in MTBI and SUMS at ASU, it's that these neglected skills of simulation and statistics are very good for helping students think about how to build models, because they can practice building models without having to have taken differential equations first. They can start to get that way of thinking. They can start to experiment. They can start to try things out. And then the last thing I have on my list for just kind of skills that students need to develop over time is, in some sense, ways of perceiving problems in the ways that applied mathematicians perceive problems. So making distinctions between linear and nonlinear problems, between discrete and continuous problems, between stochastic and deterministic problems, where they look different because the complexity is different. What they can learn about things is different. And so that categorization, that thinking about, kind of identifying basic approaches is a way to start with, here's the problem that I want to solve. I'm interested in climate change. What's the best approach to that? What are the payoffs of working in these different categories? And then maybe I want to build a simulation, or maybe I want to build a differential equation. But now the power to make those decisions is with the student, because students have to practice making those decisions. And learning how to make decisions is the hard part.
So I'm thinking back to what your question of just how do you infuse math in these environmental topics. It's fun. I mean, you're saying all these things. I'm thinking about it from a much lower level, like the 9th grader, not something about high school age. And I think about the students that don't go to college, and I think I really want those students to be exposed to the math with this. And when I say math, I'm talking more about number sense, just having an understanding of a percent. And I know that's really basic math, but having that number sense, I think, is very important to be able to make those analogies that you had earlier. And I like the idea of trying to work with pre-service teachers and helping, if we show them the connections and that they can bring those to their classroom. I like going into the classroom, but I feel like that only reaches so many. But if we can help teach teachers how to use this. And when I say teachers, I don't just mean math teachers. I think it could be in a civics class, it could be in a science class, it could be in a variety of different classrooms, which I think makes it even harder to, what resources do you develop? Because there might be stuff out there for math or for biology or something, but how do you connect these? And then it goes with earlier what we were talking about, how do you work together? I don't know, we can maybe talk about the collaboration of that. I know right now I'm frustrated that I will potentially be teaching a math and sustainability freshman seminar, but I want to do it together because I don't feel qualified to do the science. But I'm not allowed to. It has to be all me. So I'll wing it. So I don't know. I think there are lots of ways. And, talking about the resources, the only ones I know about are the ones that you do, Mitch. The PS Future stuff, and I know David's told me about a lot of environmental science that maybe hopefully we can adapt the math to. Yeah, those are resources.
I read that. I wasn't sure where this question was going, so I too am very, very much in the weeds. One of the things that I find very frustrating is that there's a clear realization that we're doing things wrong and that we are graduating a group of quantitatively illiterate students, even those that have been through a rigorous program of science. We certainly are graduating many students who are proficient and ready to go on and do great things, but clearly the studies show that we have a problem. And so I think that sometimes we say, what is the kind of math that we would like them to know, and how do we teach this to them? And I guess I would argue that, to me, that's completely the wrong approach. I think the approach that we need to take if we want to infuse mathematics into high school science, and I say that clearly because I'm talking about a very small part of this question, is that we need to go online and we need to look at the curricula for whatever state one is interested in. We need to look at the SAT tests, for the subject tests for the various scientific disciplines. And then rather than say, how do we teach these principles in mathematics in high school science, we need to turn it around and say which mathematical principles, which ideas best fit the existing programs. And I think that that's something that's very hard to do. It's something that science teachers can't do. I certainly can't do it. I have some vague idea that I look at an article that has lots of equations. And to be honest, one of the things that changed my teaching was 20 years ago going to the BioQuest modules. And I'm old enough that I learned island biogeography shortly after it appeared as an idea. And of course, there was a graph with 2 lines on it, so there had to be some math behind it. And since I was already teaching island biogeography, it was interesting to dissect the graph and learn how to generate the lines, and then take the next step and learn how to do that in Excel, which meant that I was teaching my kids a lot of math and I was teaching them a little bit of spreadsheets. But I don't care about that. I was teaching them about island biogeography, and the math was very secondary. And I understand that's probably not the right thing to say in this room. But I think it's important because most science teachers are willing to use math, but we want to use it as a tool. And we'd love to have the box be glass, but if it's a black box, we'll use it. And I think that that's how we can serve the mathematical community. But I guess we need, I think, as a community interested in infusing mathematics into the teaching of planet Earth, we've really got to start with the science and then move on to the math later.
Thanks, David. With Cubes Hub and other kinds of things, and the DIMAX group has produced wonderful things, University of Maryland with Biomath Workbench and so on. I think Lou's site had oodles of things on Math Bio that Lou said that your first workshop here at Tennessee was 92, 93 on Math Bio, and for years we were doing all of these conferences. There's an abundance of materials that integrate math and bio for education. And so the real issue is, how do we break teachers out of the habits of not invented here, and that you have to do it yourself and repeat it and so on. But how is it that we help people to adopt, adapt, and implement curricular materials that are appropriate for their students, their subject matter, their institution, their statewide requirements, et cetera, that by helping them have a kind of model of thinking about the local instantiation is a very creative process that we are co-participating in it. And for those of us who are national developers, that we're serving them, helping their students, that we do not bring the answer of how to do this, but we are co-constructing in terms of a community of how do we do this together. But I think this language of helping them understanding to do your homework, look at what's out there. Carrie's talked a lot about kind of having the Amazon kind of vetting kind of thing, that you have a user community. This worked for me in this context with my students for this. And helping... Allrecipes.com. Right, yeah. And those are the kind of metaphors that begin to work. So I really think it's having a different kind of sensibility. Is, yes, we will all generate more new and exciting things, and it's fun, but that's helping your students build those kind of models and so on. But that there's an enormous amount of material that's fully available that we can begin there and think about it. It's not a paucity.
I'll just make 2 comments on this, and they're related to each other. I think with the advent of the Common Core standards in mathematics, there is a sense on the part of math teachers, K through 12, but in particular in high school, that there's no room to do anything other than the mathematics prescribed in the Common Core standards, except possibly until 12th grade, at which point getting them to think mathematically, to pose problems and pose solutions to problems is probably too late. The next generation science standards were far more thoughtful and reaching, I will say, not to antagonize anybody involved with the Common Core math standards, but in the sense that they believed that these standards, even though they were science standards, were part of an integrated curriculum, K-12. And that part of it is to think computationally, to think mathematically, to think analytically, And so you'll see very real descriptions of what we in mathematics might have thought were mathematical problems as representative of science. And so part of what I think our role and task and everything else in this whole landscape probably is to be able to provide advice to teachers who really want to do some of these things, to do problem solving related to math of planet Earth or to planet Earth in general, in an environmental class, a biology class, whatever, want to use some of the materials that John mentions are out there and simply don't know how to do it in the context of the work environment that they're in. At the college level, one of the more interesting things that has occurred in the last year is we are winding down the biomath project that DIMAX has actually had for 11 years. And we are now obviously far enough out, so we're getting college biology teachers as well as college math teachers sending emails, calling us, asking, particularly me, questions about, and this is particularly the case of biology teachers, we've got students coming wanting to know where the math is in the biology class. Or we've got math people saying, why are you teaching this, awful college algebra course when you could be doing some of these interesting things that we did as high school students and expanding on it. So I think one part of the message during this particular time period is the boundaries between high school and college particularly are blurring rather dramatically, and that to a large extent the high school students will be pushing the colleges, and at the same time the high school teachers have to learn ways that they can deal with some of the impact of standards and pressures depending on their location, of things like, do you talk about DNA or is that too close to evolution and things like that. So, but in a matter of less than a week, when we made available all the biomath modules through COMAP, and there are 20, actually probably 22 of them, we had calls from over 500 high school teachers around the country. They sent emails saying, I want access to these modules. That's 500 teachers, beyond the pale of anything we ever thought was possible. And yet it only has really just happened because things have evolved to the point that they're interested in it, as well as we can actually make them available electronically for free, which makes a big difference. But I think the same thing is true with the BioQuest materials and some of these other materials, is that people are thirsty and interested in getting them. But back to the college level for a minute, and I think some of the people in here are very interested in, as part of research experiences for undergraduates, having problems that undergraduates that can work on that themselves are interdisciplinary. And because you usually have math REUs and you have biology REUs, you don't have the blend. Has anybody been able to come up with ways of thinking about that and infusing it into REU programs? John?
Well, actually, we're here at the home where they hold a national conference every year for undergraduate biomath kind of projects. And how many years have you been doing it here, Kelly? 7th year. And this is truly a wonderful thing if any of you get the opportunity to come with your students to present. And these students do fantastic work. And I've seen it at the high school level as well, that engaging students. And one of the great things and opportunities of working in an interdisciplinary environment is that very frequently when you build these teams of math and biology students, they can be working on problems that are very realistic and really make some headway. That very frequently that what the undergraduate, say, an engineering or math student working with a biologist, is part of the significant research of many of the biology faculty. and for many of the math students to really realize how important the skills that they have are, and for the bio students to work in a team that they're really doing this. But unfortunately, the UBM program is no longer funded per se by NSF, but many of the undergraduate research programs have embraced it. We've kept the Howard Hughes Medical Institute Quantitative Biology Workshop. Will be in North Carolina next summer in terms of doing this, and a lot of the folks involved with that are undergraduate math bio research. But let me pick up on one other thing you said, Mitch, if you may. In biology curriculum, and I'll take David's example of something like island biogeography, it's usually not there in the general bio course. And yet, if you take an upper level ecology course, it is. And so one of the things that has been difficult for many students in the undergraduate biology curriculum is the dissonance between a genetics course where you're doing population and quantitative genetics, you're doing an ecology course with population ecology, you might be doing a bioinformatics course with hidden Markov models or something like this, and there's no bridge. That they go from this kind of beginning textbook with no equations, no graphs, no data, to all of a sudden then they're in the subject-specific areas, and they have automatically, they're supposed to have all of these skills. And so this comes back to my thing of, in terms of the metacognitive growth, that this significant dislocation, when you haven't explicitly thought about how do you create the bridge to help students navigate your own curriculum. And I think that it's at that curricular level that in the planning of a course, the planning of a year, the planning of an undergraduate curriculum, that we have to be aware of the kind of learning progression and what are the steps there that can be helpful. Lou's got a response already. Can we get a microphone to him?
I want to take over.
Here's Chris.
So at the
It's not up yet.
So at the undergraduate level, the biology community, of course, created what's called the Vision and Change report. There's two of them now. The second one just came out. And it really did encourage a curricular perspective of key biological concepts as well as key quantitative concepts that went along with it. And there certainly are institutions, many institutions now, which are taking, as John pointed out, a curricular perspective in which you trace through the curriculum, the undergraduate curriculum, what are the key quantitative concepts that should be incorporated at different locations, what are high priority and should be potentially repeated several times in different manners throughout different courses, and what is appropriate to include in a formal quantitative course, like a mathematics for life sciences course, which we do here, or a statistics or a biological data analysis course, and places like Macalester College. Is there anybody here from Macalester? Well, you were lucky. You grew up next to a great institution. And folks at Macalester have actually...
Augsburg produced Nobel laureates like Peter Albrecht.
So what they have done is go through and carefully document where these concepts are throughout their curriculum and what is repeated, and then they take the step of seeing from a history of what courses the students took, what their trace through the curriculum was, and whether or not the exposure was appropriate. And I would encourage that perspective with any undergraduate program. It requires work, though. It requires a faculty that actually is going to invest time and effort in thinking about the curriculum and not just about who's teaching this course next semester. And unfortunately, a lot of... now Carlos is going to tie in because he's going to give another example.
I just want to talk about undergraduate programs that involve biologists and mathematicians. We have one doing 20 years. It has produced over 110 PhDs 70% are from underrepresented groups. Almost if you look at any Latino that is doing math biology in the country, almost all of them have gone through that program. So this has been done. But what is interesting is, and in fact there are two here, and one is Anarina Murillo, psychology major. She graduated on the undergraduate degree in applied mathematics in the life and social sciences after she got her degree from biology. And Claudia is another example. All of them go through this program, and you also went through that program. He went through, anyway, but
best programs I've ever seen.
Yeah, but anyway, but the point is that the students choose their questions. So they ask questions: what is the impact of alcohol on the brain? Or what is the impact? What are the dynamics of bulimia? We don't tell them the questions. And one of the things that they learn is that the faculty are not very smart and that they know much better than the faculty. And I think that that's at the crux of the matter. We tell them what to do. We don't want to hear what they want to do because we can't react to that. We really don't. So Steve Strogas wrote a beautiful paper in the New Yorker in 2003 where he talks about the real heroes of 1953. That's when Watson and Crick discovered the chemical structure of DNA. And he talks about, in fact, that there is not only one way of doing science, which is part of the problem. I think that's what Carlos said. But actually many more ways of doing science. And he talks about a third way of doing sciences. The first I assume is the scientific method. The second I assume that he was talking about pencil and paper. And the third one is the computer experiment. And he says, what did they do? Fermi, Pasta, and Ulam, very smart people, right? They thought that they understood some linear dynamics, or let's say some nonlinear couple oscillators. And so they said, well, we know what's going on. They put it in the computer, and it turned out to do that they were completely wrong. This is what this is about climate change and things like we were talking about that. We had very, very smart people that think exactly what's going on, then they put in the computer. But then they said, this is a third way of doing science, because you can use the computer as a telescope to understand the dynamics of stars. You can use it as a microscope to understand the dynamics of cancer. And he says, there is no way that we're going to be able to find any cures of cancer or any other diseases unless you have biologists and computational scientists working hand in hand. That's sort of the best. And now there is a fourth way of doing science, and this data science. That has to be data science. And so the fact of the matter is we continue to teach only one way to do science in high school, and that's exactly the problem. And the problem is not really because they might not know. It's because many people, it's just very, very difficult to learn different ways of doing science. But the most important lesson here is that Fermi, Pasta, and Ulam, three great researchers, got it all wrong. So when we say that we understand what's going on with climate change, what is creating this, there is a lot of uncertainty. And one of the biggest problems that we have today is the tremendous levels of uncertainty that we have in everything that we do. And the way we teach that, there will be a lot of dialogue about things that, in fact, the uncertainty should be accounted for, and students should be able to learn about that we are not certain about many, many things, even though the overwhelming evidence in the case of climate change might be there, we're still not uncertain, just like when the CDC predicted a million cases of Ebola by January. And I think they were wrong. I think now there is still about 10,000. This is the kinds of mistakes that we make also as a scientist, as a computational scientist, and we have to be aware of that.
It's dangerous to give it back to me, so I'm just going to.
We have an extra chair if you want to join us.
No, everyone should join us, right?
Well, actually, do others have comments from the audience about the discussion we've been having here? Christiane.
Yeah, I have some comments, in fact, around the curriculum. I think one problem in secondary school is that the message should be that we are given a toolbox, and we should learn to use the tools out of context. And in fact, even the present tools are very, very useful. Well, I wrote a book, Mathematics and Technology in Springer, just with all the applications we have with the usual Euclidean geometry, where I talked of the GPS, and you want to put your antenna in cellular phones. How do you distribute them so that you have the least possible? Many things you can do. In fact, you were mentioning, okay, the things that go to algebra, number theory, ring theory. Well, these are, if you look to computer science, you have an error correcting code in your cellular phone that use them. So in fact, computer science is also applied mathematics, and there you use you use the number theory for cryptography, you use the ring theory for the error correcting codes. So there are a multitude of applications. The problem is to disconnect. I think we should message in secondary school is that mathematics is a living discipline. And in fact, the kind of things that interest the kids are electronic devices. So you just open your computer and then the image is encoded by JPEG. How does it work? And then you have the cryptography, and then you have all these things. So we have to, but I could say there is not a unique choice for the curriculum because there are many ways. But really the skills we have is that it has to be, it's a toolbox, and we have to show problems where we use the tool out of context. Just an announcement. The website of Mathematics of Planet Earth, which is still online, contains, so the idea during all that year, we wanted to collect curriculum materials, but also resources for teachers. So people who want to some resources, you should go there and see what you find. People that produce resources, if your resources are not posted, then contact us, and we want to have, because it's where do we find the material? Well, that was one purpose of the website and maintaining after the end of the year, is that it's a repository for all the material that can be useful, and we want this material to be developed over the years. So we hope that all of you, you contribute to the website.
I have to follow up on that because you're sitting next to Olivia, and that there is a wonderful math reform project that's built on the game Sudoku and showing how it relates to CAT scans, MRI, and so on kind of thing. But it's also part of this STEAM movement of putting arts into STEM education kind of thing. And that in terms of kids thinking that games are fun and doing this kind of stuff, but I was telling Olivia that one of the programs for bringing undergraduates into research is in general bio courses. Sally Hoskins has a program called Create and Consider, Relate, etc. But one of the things they do is they literally cartoon the kind of article to get a sense of what's going on, what they're trying to do, and so on. They do storyboarding, they do concept mapping, etc. kinds of stuff, annotating graphs, etc., and unpacking what this kind of research is. But I think very frequently that something like number theory is something that's viewed as esoteric and inaccessible, and yet here that engaging them with somebody might already be inevitably that somebody's a Sudoku solver in your class. They would never perceive it as mathematics. And I think it's those affordances that we have to connect with their social life, so 6 degrees of separation, to be able to deal with their artistic life, their musical life, their athletic life, et cetera, that all of these are important. But I particularly enjoyed you bringing up about this beautiful notion of number theory that has been very much popular.
So I have to chime in here as well, because in some sense what you just described is one of the hardest unsolved problems in mathematics education. And that is, how do we get students to realize that a tool can be used for more than the context that they learned it in? And so there are quite a few examples of this sort of difficulty. One of the most famous is Carraher and Carraher, and the study of Brazilian nut sellers, so children in the streets who sell nuts. And they're incredibly good at doing arithmetic and making change and making sure that they're not cheated when they're in the street selling nuts to customers. But if you put them in a classroom setting, and they did go to school, and ask them the same problems in a classroom setting, none of them could solve the problems at all. And so this issue of changing context makes things different to people is very real. And we don't really have any good answers for how we can say, teach students about a technique in one context and have them realize that that technique can be used in other contexts. So students are very good at saying, oh, proportion, yeah, I use that for mixture problems. But to take the inverse of that, to say, okay, you have a problem in sustainability, what mathematical techniques are going to help you out here? That is incredibly difficult. And that's one of the things that we have very little understanding of how people do it or how to teach it.
Again, to get to the realities, I absolutely agree with you that we need to do that. We need to excite the kids about math. 6 years ago at my school, we decided we were going to create a STEM program that integrated math and science, and we were going to put 2 teachers in a classroom together. One was a chemistry teacher, one was an algebra geometry teacher. Ridiculously expensive. In a small school, to double staff a class is a tremendous drain on resources. They actually had to bring in 2 extra people. And they worked at it. I was involved with it very much in the background. I went out to the National Science Teachers Association conference, the theme of which that year was integrated STEM education. And as usual at the conferences, most of the interesting stuff happens at 6 o'clock when everything's done. And I was together with a bunch of teachers, and they said, oh, we tried that, it failed. And that was the common theme. When we got back to Groton, we had real problems, and the biggest problem was that in order to do this effectively, both the math and the science teacher had to give up significant parts of their curriculum, and because of the unwillingness to do so, 3 years later we've abandoned it completely. And to me the challenge, I would love to go talk to geometry class about some of the landscape ecological work that I do, and I think that there would probably be some kind of relevance of that to what they were studying, but there's no way the math teacher would give me enough time to do that. What they'd like me to do is come in and give a 5-minute presentation, which doesn't really serve science or math, I don't think. And I guess the challenge that we are putting to our math teachers is, what are the critical parts of your curricula? What can you abandon to allow for the more creative, integrative approach? And the answer we're hearing loud and clear is that everything is important. And that I spend enough time with teachers around the country that that's the standard response of a high school math teacher. Everything is important and I can't give anything up.
Mitch, can you say something about the high school you told us about?
Yeah, we had a writers meeting, and both Trina and David are writers on the Planning for a Sustainable Future module project that we have, and we needed another school to do field testing, and waited to see if the project was funded before we tried to enlist a school. And so this summer I spent a little bit of time at T.C. Williams High School in Alexandria, Virginia, and many of you probably know of it, most famous because of the movie Remembering the Titans, which was about the football team at T.C. Williams. But it's a very large high school in Alexandria. It's grades 10 through 12. It's ninth grade. Alexandria's ninth grade school is a separate school about a mile away. So, but the one thing that was interesting is that the entire high school is interdisciplinary now. They've managed to hire only teachers, basically, who are willing to co-teach, and they've figured out scheduling and everything else so that they can co-teach. And by that I don't mean just math and science. I mean history, social studies in general, language arts, and so forth. So their questions to me, if they were going to be field testing some of our modules, and our modules are primarily a week to 10-day modules, was there a place in the modules that could bring out the language arts component of it? Was there a place in the modules that could bring out the social studies aspects of it? Because they've been doing it now for 3 years, and their biggest problem is finding materials that really truly integrate. So it's almost the opposite of what David said about schools dropping it. But it may also be the fact that it's a huge high school, and it's the only high school in Alexandria, so there isn't a choice for kids if they want to go someplace else without spending a fortune to do it. So, but it is it'll be interesting for us to follow the path of these modules and their field testing from a vantage point other than to see if the modules work and all the evaluation tools that we put in place at the same time. But following Carlos's comments, there's a number of projects, mostly funded by NSF, research projects on what is called cognitive transfer. And whether we intended it to be or not, we were talked into it by NSF. There's a huge cognitive transfer research, like half the funding for the project goes to researchers looking at whether you can design materials, which is what we're trying to do, to facilitate cognitive transfer. So stay tuned. A few years from now, I may be able to report back. But it has been not a totally unsolved problem in math education, because people like Jim Greeno, who are older than some of us, were working on this particular problem, but it has heightened interest in both the research community but also primarily in the mathematics community, as the separation between what we might have called pure math and applied math is not as dramatic as it once was. So as you move into this applied mode, cognitive transfer seems to be even more important. But it will be interesting to see, given that these are modules designed for sustainability, and they're math, bio, math, environmental science modules, to see if we can build in from scratch cognitive transfer. And we have a team of full-time researchers working on it. So, question?
I think she had her hand up first. She's had it up for a while. I'm trying to be very... No, go ahead.
Unless it's a quick question.
Do you have a quick question?
I don't know. I can take as much time as you want, but I'll let you have it first. Okay.
Well, thank you. Okay. I just wanted to kind of add on to what David kind of brought up in the high schools. I don't teach high school, and I'm trying to remember back. It's been a while since I've thought about the math component of the high school curriculum, but I think you might have most success if you sort of pick the appropriate class to try to sort of co-teach with somebody in science. For example, in our small liberal arts college, we have a math for liberal arts class where it's very free. If I was to ditch half the material and teach something else, it really makes no difference, and somebody might not even notice. But if I do that in a calculus class, if I do that in Calculus 1, the students that are going on to Calculus 2 are going to have some big problems. There's going to be some big problems with that. So that's kind of all I wanted to. And for example, in some upper level classes as well. So for our math ed majors, if they have to take classical Euclidean geometry, for example, they can't just ditch half the material and study something else. There is, certain standards that they have to kind of go by, and that's kind of all.
Actually, I'd like to follow up on that because one of the most interesting papers I read was a Lukens 2000 paper that combined AP Biology and AP Calculus, and the results were that the scores in that combined co-taught class increased over the traditional, and that's a kind of curriculum that you can't drop things. So I think that may be a little false that you can't drop things. I think that has to be challenged, especially in light of those results. I think it's a really great article. There are a lot of other things I want to say. Early programming. I have a really good friend who grew up near Silicon Valley, and in her school, they do programming early, like really early as a kid. And I thought, what a wonderful thing, and what a way to open doors to people that don't have prejudices already about how well they know math or not. And I would say Common Core, I'd push back a little and say that there is a lot there are objectives that students have to make, but they're not told how. And I think what I see in my own children's curriculum in the school is early statistics and early data interpretation. It's wonderful what they're doing in kindergarten, making bar charts for weather days that I'm doing in the first week of my college statistics class. So I'd push back and say I think there's a lot of opportunity. I have really liked seeing it. And the parents, I think, actually are also something. I half joke, that one of my outreach jobs is to help parents of fifth graders on Facebook help with their kids' homework. And I call it teaching 2 generations at once. But the other thing goes to resources. You mentioned the MPE site. Also, the CERC has a really great site that you can filter by various subject areas. And so I've even used them, as well as Cubes Hub. You can filter by mathematics topic, or by sustainability science topic on the CERC site.
I want to comment about some of the pushback that's been discussed here in a different way. You can change the culture. We had a requirement at a previous institution I was at that every faculty member, when hired, had to do 1/6 of their teaching outside their discipline. It was the smartest rule we had at the place. You hire a different kind of faculty. We had, secondly, another requirement that 2 members of the search were outside your discipline and frequently outside your division. In other words, you're coming to work for the institution, you're not coming to work in the silo. And thirdly, that our motto was, first we teach students, second we teach life, only thirdly do we teach a subject matter. That putting the kind of priorities in, so I urge you, sit on those kind of things. But administrators can be your friend, and as much as we frequently view them as the dark side, this has been a president of a university and a provost. She's been an NSF officer. Lou and Carlos, you've built these incredible kinds of institutions, as has Fred, kind of thing. It takes somebody to bring a village and to support that village and make it happen. But part of it is this very careful hiring and commitment and so on. And you can do things that you talk about the expense. And so we literally will go and argue with economic models. Okay, each of us had for these 2 classes 18 students. If the 2 of us team teach a class where we have a minimum of 36, how is your economics any different, kind of thing. But we do things like surreptitiously schedule 2 courses to occur at the same time in the same building in adjacent classrooms, and that somehow our students could navigate and go between them and so on. The registrar who was anal missed it, that somehow we were doing curricular deviance, etc. But I want to make one final comment is one of the things in AP Bio, we were fighting the same thing you were talking about in environmental, and we looked at what the calculus reform had done, and many of you might attack AP calculus, but it had made enormous kind of differences compared to what previously existed. And we said to Bio, we're not asking you to do what we loved. We saw AP was actually doing studio art where students were coming in with juried kind of things. And that would be our goal. We'd love to do that. Okay, you're not going to do that, but do as well for us for Bio as you did. And so we fought for 12 years that if you would used to go to Walmart or Kmart and you'd buy a calculator and it said it's good for AP, but then there'd be an asterisk, not for biology. And so 90, 30, 30, 10 is not a math problem. That's a memorization problem of a pattern, kind of thing. How do you deal with real data and ratios and statistical tests? So we fought for calculators, we fought for spreadsheets, and if you're going to do bioinformatics and contemporary biology, we had to have access to the internet. I would argue that getting that in, getting evolution in every chapter rather than the isolated chapter they could avoid, and fighting that the teachers had 15% of the time to creatively do what they loved rather than a prescribed curriculum. Those were the victories. And it's hard work serving on these committees because you're minority voice almost all the time. But I urge you, participate, change the policy at your institution, work for differences in terms of hiring practices and policies that are progressive that support interdisciplinary work. Thanks, Mitch.
I think we're running out of time, so one last comment from the panel.
Okay. So one short and one slightly longer. The shorter version is, since you brought up test scores, I have a very nice short story about Arizona State University, and when they took rational functions out of their pre-calculus curriculum, scores in rational functions went up. And there are good reasons for that, and you can ask me about it. But the other thing, one of the questions that was on the sheet that I don't think we had time to get to was talking about resources. So I did want to spend a little bit of time talking about resources. At the graduate level, Otto and Day is a very interesting textbook that spends a couple chapters on how to build models, and that's kind of an interesting topic. At the middle school and high school level, looking at building models, I mentioned them before, but I'll mention them again. Uri Walensky and Mitch Resnick looking at simulations and how you get students forming hypotheses and thinking about biological systems in that very open-ended modeling way. The other thing I want to talk about is those are kind of the wild, uncontrolled things where you don't necessarily know what students are going to come up with and what mathematics they're going to be using. There is some work in constrained open-ended problems of here's a problem where students need to build hypotheses and they need to come up with models, but you know in advance what models they're going to come up with. In particular, physics education and engineering education are very good at this. They are miles ahead of mathematics education in that area, so they are worth looking at their resources for inspiration. And then Richard Lesh and just kind of the Illinois group in general has done a lot of work on how you design what they call model eliciting activities, which is that sort of thing. How do you design an open-ended question so that along the way students invent ideas of proportion, for example? So those are good resources to look at for, I want students to have an open-ended experience, but I also want to make sure that they learn this topic.
So John said something that reminded me of a committee I'm on. The business calculus class that we teach they've now told us we used Excel, we used Maple because 10 years ago they said we want more technology, and now they're saying they want no technology because they don't know the skills, so we need to revamp the course to go back old school. So thinking about, what impact do the changes we make have? And I feel like our position is we do whatever they say because it's a service class, so I feel like we're trapped on that one. And there may be other situations you get trapped on. So that's kind of a negative note. On a more positive note, at some point in this conversation I was reminded of the Mega Moody competition for high school students, which is awesome. A modeling competition. It'd be wonderful. I don't know who creates these questions, but it'd be great if there was a sustainability issue question for that contest.
That's the COMAP contest.
It's not. No, the Mega Moody is a SIAM.
Right. But COMAP has its math modeling.
And that's for college students. Oh, they have for high school
No,
too?
they have one for high school students too now. And the question is this coming up, our sustainability? Maybe giving us ways. I don't know that it'll help anybody to know the area.
I guess I would just end by saying that I think that dealing with high school curricula is just a lot of banging your head against the wall a lot of the time. However, the most important point, I think, is that when we teach environmental science, when we teach climate change or resource management, when it's done quantitatively, it is very clear that the kids gain a much greater understanding of the subject matter. They're able to argue much more articulately and compellingly. So I very much hope that all of these initiatives and all these organizations pay off.
Mm-hmm.